What if I told you that quantum computing just quietly passed a milestone as important as the invention of the transistor itself? Not in a lab demo, not in a press release from a startup chasing headlines, but in the pages of science from some of the most respected physicists on the planet. They're not saying quantum computers work yet. They're saying something far more consequential, that we now know how to build them. For decades, quantum computing has lived in a strange kind of purgatory. It's been the technology that's always 10 years away, no matter what year you ask. Skeptics have rolled their eyes at the endless hype cycles. True believers have promised a future where quantum machines crack encryption, design miracle drugs, and simulate the universe itself. And somewhere in the middle, actual physicists have been quietly grinding through decades of unglamorous, incremental work, trying to coax something coherent out of particles that seem to actively resist being observed. But in December of 2025, that quiet grinding produced something loud. A team of researchers, led by David Aushalom, a professor of molecular engineering and physics at the University of Chicago and the director of the Chicago Quantum Exchange, published a paper in the journal Science that reframes the entire conversation. The paper wasn't written alone. It brought together some of the biggest names in quantum research. Scientists from the University of Chicago, Stanford University, the Massachusetts Institute of Technology, the University of Innsbruck in Austria, and Delft University of Technology in the Netherlands. When institutions like these come together to co-author a single perspective piece, it's worth paying attention. This wasn't a marketing document. It was closer to a State of the Union address for an entire scientific field. And the central claim in that address is almost audacious in its simplicity. Quantum technology, the authors argue, has reached the same inflection point that classical computing reached in 1947, the year the transistor was born. To understand why that comparison matters, you have to go back to that moment. On December 23, 1947, a small team at Bell Labs, John Bardeen, Walter Brattain, and William Shockley, successfully demonstrated a strange little device made of germanium. It amplified an electrical signal using a solid-state material instead of a bulky, fragile, power-hungry vacuum tube. At the time, almost nobody understood what they had just built. It wasn't a computer. It wasn't even a product. It was a laboratory curiosity, a proof that a certain kind of physics could be harnessed in a certain kind of way. There was no assembly line. There was no roadmap. There was just a working demonstration that the underlying science was sound. What followed that demonstration is the part of the story most people forget. The transistor did not immediately reshape the world. It took years of material science, years of manufacturing innovation, years of trial and error before transistors became reliable enough, cheap enough, and small enough to matter. It wasn't until the 1950s that engineers began building computers out of discrete transistors, and even then, the process was almost comically manual. Memory made of tiny magnetic cores, threaded by hand, with solder joints made one at a time by graduate students and lab technicians. It took until the 1970s for Intel to start producing integrated chips with thousands of transistors on a single piece of silicon. It took another 2 or 3 decades after that to break the million transistor barrier. Today, a single high-end processor can contain tens of billions of transistors. But none of that scale was inevitable. It was earned slowly through a specific kind of patient, coordinated engineering effort that followed the initial scientific breakthrough by years, sometimes decades. That's the pattern the new science paper is pointing to. According to Aushalom and his co-authors, quantum technology has now reached its own version of that December 1947 moment. The foundational physics has been proven. Functional quantum systems exist in laboratories around the world. What's needed now isn't some undiscovered breakthrough in fundamental theory. It's the coordinated cross-sector engineering push that turns a laboratory curiosity into an industrial reality. Aushalom put it directly. He described this as a transformative moment in quantum technology, one reminiscent of the transistor's earliest days. And if you sit with that comparison for a second, it's a genuinely bold thing to say. It means the authors believe we are no longer arguing about whether quantum systems can be made to work in principle. We are now arguing about how to engineer them at scale, which is a completely different and in some ways much more solvable kind of problem. So how did the researchers actually back up a claim this big? They didn't just make an assertion and move on. They did something methodical. The paper surveys 6 of the leading approaches to building quantum hardware. 6 fundamentally different physical platforms that scientists have been racing to develop in parallel for years. There are superconducting qubits, the approach used by companies like IBM and Google, which rely on tiny circuits cooled to near absolute zero. There are trapped ions, where individual charged atoms are suspended and manipulated using electromagnetic fields. There are spin defects, which use tiny imperfections in materials like diamond to store and manipulate quantum information. There are semiconductor quantum dots, which borrow heavily from the manufacturing techniques of the classical chip industry. There are neutral atoms, arranged in precise optical grids using lasers. And there are optical photonic qubits, which encode information directly into particles of light. For each of these 6 platforms, the authors evaluated something called Technology Readiness Level, or TRL, a scale originally developed by NASA to describe how mature a technology is, running from early theoretical concept all the way up to a fully proven system operating in its real-world environment. What's particularly interesting, and honestly a little bit meta, is how they assessed these readiness levels. The researchers used large language AI models, specifically tools like ChatGPT and Gemini, to help analyze and compare the relative maturity of each platform across 4 different application areas: computing, simulation, networking, and sensing. Think about that for a moment. A landmark paper about the future of quantum computing used today's most advanced classical AI systems as an analytical tool to make its case. That's not a footnote. That's a small, quiet signal about where we actually are in the broader technology landscape. 2 revolutionary computing paradigms, artificial intelligence and quantum computing, already beginning to intersect and support each other's development. The results of that analysis were not uniform across the board, and that's important, because it tells us this isn't a story about one winning technology, it's a story about specialization. Superconducting qubits scored highest for computing applications, which lines up with what most people already associate with quantum computing: the big, headline-grabbing machines from companies racing toward quantum advantage. Neutral atoms scored highest for simulation, the kind of work where you use a quantum system to model the behavior of another quantum system, like a complex molecule or a novel material. Photonic qubits, which travel at the speed of light and don't require exotic cooling to move information around, scored highest for networking, the eventual backbone of what people are already calling the quantum internet. And spin defects scored highest for sensing, an application that doesn't get nearly as much public attention as quantum computing, but which may end up being one of the earliest commercially useful branches of the entire field, powering ultra-precise measurement devices for things like magnetic field detection, medical imaging, and navigation systems that don't rely on GPS. This is one of the most important and most underreported parts of the story. Quantum technology is not a single race with a single finish line. It's a set of at least 4 distinct races, each with different leading contenders, each maturing at a different pace, and each likely to reach commercial relevance on a different timeline. The public conversation about quantum computing tends to collapse all of this into one simple narrative. Will quantum computers break encryption? Yes or no? When? But the reality the researchers describe is far more nuanced, and honestly, far more interesting. Now, here's where the paper gets refreshingly honest, in a way that a lot of technology hype pieces conspicuously avoid. One of the co-authors, William D. Oliver, a professor at MIT and the director of its Center for Quantum Engineering, offered a pointed caveat about what these high TRL scores actually mean. He pointed out that back in the 1970s, semiconductor chips of that era could reasonably be described as fully mature, fully proven technology for their time, essentially a TRL 9, the highest rating on the scale. And yet, those chips, by any modern standard, could do almost nothing. A processor from 1975 is not remotely comparable in capability to a processor from today, even though both might have been considered technologically mature within their own eras. In other words, a high readiness score is not the same thing as a finished, all-powerful technology. It means the engineering fundamentals are proven and repeatable. It means you can build the thing reliably. It does not mean the thing has yet reached anywhere near its ultimate potential. Oliver's point is essentially a warning against overclaiming, a reminder that reaching the transistor moment doesn't mean we've reached the smartphone moment. There's an enormous amount of runway between a proven concept and a mature, ubiquitous technology, and that runway is measured in years and decades, not months. So if the science is largely settled and the readiness levels are climbing, what exactly is standing between us and quantum computers that matter in daily life? The paper is refreshingly specific about this, and it's worth walking through because as the obstacles aren't the kind of thing you'd expect from science fiction. They're engineering problems, the unglamorous kind, the kind that quietly determine whether a technology actually reaches the world or stalls out in a handful of research labs. The first major obstacle is material science and fabrication. Building a functional quantum computer requires an extraordinary level of consistency and precision at the physical, material level. Every qubit, no matter which of the 6 platforms you're using, needs to be nearly identical to its neighbors, because tiny variations in material purity, in fabrication tolerances, in the placement of individual atoms can introduce errors that cascade through an entire system. Classical computing solved this problem for silicon decades ago, through a combination of relentless manufacturing refinement and enormous capital investment. Quantum computing is now facing its own version of that same challenge, except with materials and fabrication techniques that are, in many cases, far less mature than silicon lithography was even in its earliest industrial days. The second major obstacle, and arguably the most vivid one described in the paper, is wiring. It sounds almost absurdly mundane, but it's a genuine and serious engineering crisis. Most current quantum platforms rely on individual control lines running to nearly every single qubit in the system. Each of those wires has to be threaded, calibrated, and managed, often at temperatures colder than deep space. That approach works fine when you're dealing with dozens or even a few hundred qubits, but the roadmaps for useful, fault-tolerant quantum computing call for systems with hundreds of thousands, potentially millions, of qubits. You simply cannot run 1 million individual wires into a cooling chamber the size of a refrigerator. The physical space doesn't exist. The thermal load doesn't work. The engineering doesn't scale. The researchers draw a direct parallel here to a problem that classical computer engineers faced back in the 1960s, a problem that actually had a name at the time: the tyranny of numbers. As early computers grew more complex, the sheer quantity of individual components and the hand-wired connections between them became the primary bottleneck, limiting how large and capable a machine could become. It wasn't a limitation of imagination or theory, it was a brute, physical limitation of assembly. And the solution back then wasn't some entirely new form of physics. It was the integrated circuit, a way of fabricating many components and their connections together on a single piece of material all at once. Quantum computing is now standing at the edge of its own tyranny of numbers, and the paper suggests that solving it will require an equally creative leap, likely some form of integrated on-chip control architecture that doesn't rely on a one-to-one ratio of external wires to qubits. Beyond wiring, the paper flags a cluster of related system-level challenges that tend to get far less attention than the qubits themselves. Power management is one. Running and controlling large quantum systems, especially the electronics needed to generate and route the precise microwave or laser pulses that manipulate qubits, requires significant and carefully managed power delivery, all while keeping the quantum system itself shielded from any stray heat or electrical noise that could destroy the fragile quantum states you're trying to preserve. Temperature control is another. Several of the leading platforms, including superconducting qubits, only function at temperatures a fraction of a degree above absolute zero, colder than the depths of interstellar space. Building refrigeration systems that can maintain those conditions while also housing increasingly large and complex quantum processors is its own significant engineering discipline. Automated calibration is a third challenge. As the number of qubits grows, it becomes impossible for human researchers to manually tune and calibrate each one individually, the way early quantum experiments often did. The field increasingly needs automated software-driven calibration systems that can keep a growing, ever-shifting quantum processor properly tuned in real time. And finally, there's system-level coordination itself. The software, firmware, and control architecture needed to orchestrate potentially millions of qubits working together coherently, executing complex algorithms without the whole system falling apart from accumulated errors. None of these challenges, taken individually, sound like the stuff of a science fiction breakthrough. That's precisely the point the authors are making. The remaining barriers to practical quantum computing are not primarily about undiscovered physics anymore. They're about wiring, cooling, power, calibration, and coordination. The same unglamorous categories of problems that classical computing had to solve on its long road from the transistor to the modern smartphone. And this brings us to what might be the most important message buried inside this entire paper: patience. It's not a word you often hear in conversations about cutting-edge technology, especially not in an era where product cycles move in months and venture capital demands rapid returns. But the authors go out of their way to emphasize it. They point out that many of the most transformative developments in classical electronics, the refinement of lithography techniques that allowed manufacturers to print increasingly tiny features onto silicon, the discovery of new transistor materials that improved speed and efficiency, took years, and in many cases decades, to move from laboratory demonstration to industrial deployment. The transistor was invented in 1947, but the integrated circuit didn't arrive as a commercial reality until more than a decade later, and it took additional decades beyond that before computing became something ordinary people carried in their pockets. The authors argue explicitly that quantum technology is likely to follow a similar arc. In their own words, they write that patience has been a key element in many landmark developments, and that this history points to the importance of tempering timeline expectations in quantum technologies. That's a remarkably candid statement to include in a paper that's also, in the same breath, declaring the field has reached a historic turning point. It suggests the authors are trying to walk a very deliberate line, communicating genuine, well-earned optimism about where the science stands, while simultaneously pushing back against the kind of breathless overpromising that has, frankly, plagued quantum computing's public image for years. There's also a structural argument buried in the paper that deserves attention because it's not just about physics or engineering, it's about how scientific progress actually gets made. The authors emphasize the importance of system-level, top-down design strategies, rather than researchers working in isolation on narrow individual components. They emphasize the value of a shared body of open scientific knowledge, explicitly warning against what they call premature siloing, the risk of different labs, companies, and countries racing ahead in isolated bubbles, each solving the same fundamental problems separately instead of building on each other's work. This is a direct echo of how classical microelectronics actually developed. The rise of the transistor and the integrated circuit wasn't the story of a single lone genius. It was the story of a tightly interconnected network of academic researchers, government funding agencies, and private industry, all working in overlapping, mutually reinforcing directions across decades. Bell Labs, universities, the US government's defense and space programs, and eventually companies like Fairchild Semiconductor and Intel, all played interlocking roles in turning a laboratory demonstration into a global industry. The authors of this new paper are essentially arguing that quantum technology needs that exact same kind of tri-sector collaboration. Academia, government, and industry moving together, sharing knowledge openly, rather than racing apart into isolated silos chasing short-term proprietary advantages. It's a subtle but pointed message, particularly at a moment when quantum computing has become an area of intense national competition, with major government investment programs in the United States, China, and Europe all racing to establish leadership in the field. The paper isn't naive about that competitive pressure, but it is making a clear scientific argument that open collaboration, not closed-off competition, is historically what allows this kind of foundational technology to actually mature. So where does all of this leave us? If you strip away the layers of nuance and get down to the core message, the paper is making 3 claims at once, and it's worth holding all 3 in your head simultaneously, because dropping any one of them distorts the picture. First, the foundational physics of quantum information technology has been proven across multiple independent platforms in multiple labs by multiple research groups around the world. That part of the argument really isn't controversial anymore among people who work in the field. Second, the challenges that remain are now overwhelmingly engineering challenges. Fabrication, wiring, cooling, calibration, and system-level coordination, rather than open questions about whether the underlying quantum physics can be harnessed at all. And third, based on the historical precedent set by classical computing, solving those engineering challenges at true world-changing scale is very likely to take years, quite possibly decades, of sustained, coordinated, well-funded effort, not a sudden overnight leap. None of that means quantum computing is somehow disappointing or that we should stop paying attention until it's finished. Quite the opposite. It means we are living through the equivalent of December 1947, watching researchers in a lab flip a switch on something that barely looks impressive to an outside observer, but that quietly changes the trajectory of technological history. The people who understood the significance of the transistor in 1947 were a small handful of physicists and engineers. Everyone else caught on gradually over the following decades as that laboratory curiosity slowly, patiently, methodically transformed into radios, then computers, then the internet, then the smartphone in your pocket right now. The University of Chicago's role in framing this moment is not incidental either. Chicago has positioned itself as one of the central hubs of American quantum research, largely through the Chicago Quantum Exchange, an initiative Al Shalom directs, which brings together the university, national laboratories, and industry partners in one of the most concentrated quantum research ecosystems in the country. That regional concentration of talent and infrastructure mirrors, in a smaller and more modern way, exactly the kind of tri-sector collaboration the paper argues is necessary for the field as a whole to succeed. It's a small, local example of the larger structural argument the authors are making on a global scale. It's worth pausing here to talk about why the skepticism around quantum computing built up so heavily in the first place, because it helps explain why this paper lands so differently than the usual wave of quantum headlines. For years, the public conversation around quantum computing has been shaped by a mixture of genuine scientific progress and premature marketing. Every few months, it seemed, some company or lab would announce a new qubit record, only for careful observers to point out that the demonstration solved a narrowly engineered problem with limited practical relevance, rather than anything resembling a useful, general-purpose computation. That pattern repeated often enough that healthy skepticism became the default posture among many scientists and journalists covering the field. People got tired of being told the revolution was imminent, only to watch the goalposts quietly move again a year later. What makes this paper different is precisely what it doesn't claim. It doesn't announce a breakthrough application, and it doesn't promise quantum computers will soon outperform classical ones at some headline-grabbing task. Instead, it makes a structural, historical argument about the maturity of the field as a whole, using a framework, technology readiness levels, borrowed from aerospace engineering rather than marketing departments. That kind of sober, methodical framing is exactly what tends to separate genuine scientific inflection points from hype cycles. The transistor's inventors didn't announce the smartphone in 1947. They announced a working amplifier made of germanium, and they let history do the rest of the talking over the following decades. It's also worth touching on what's actually at stake if this assessment turns out to be accurate. Practical, large-scale quantum computers could eventually reshape fields as varied as cryptography, where new quantum-resistant encryption standards are already being developed in anticipation of future quantum code-breaking capabilities and pharmaceutical research, where quantum simulation could model molecular interactions with a level of precision that classical supercomputers simply cannot reach no matter how much raw processing power gets thrown at the problem. Quantum sensing, the category where spin defects currently lead, could eventually produce navigation systems precise enough to function without satellite signals at all, along with medical imaging tools sensitive enough to detect disease at scales far beyond what's possible today. None of these applications are guaranteed, and none of them are imminent. But they're the reason a paper like this, quietly published in an academic journal, ripples outward into broader conversations about the future of technology, national competitiveness, and scientific investment. It's also worth sitting for a moment on just how unusual it is for a paper like this to emerge as a joint statement from 5 major institutions, rather than a single lab's press release. Perspective pieces published in a journal like Science, especially ones spanning this many top-tier institutions, are not written casually. They represent a kind of consensus statement, a moment where a field's leading voices agree it's time to step back from the day-to-day grind of individual experiments and say something bigger about where the whole discipline actually stands. That in itself is a signal worth paying attention to, independent of any single technical claim inside the paper. When researchers who normally compete with each other for funding, for talent, and for headlines come together to co-author a unified assessment, it usually means something structurally important is happening beneath the surface of the field. So what should you actually take away from all of this? Not that quantum computers are about to appear on store shelves, not that encryption as we know it is about to collapse overnight, not that the science fiction future of instantaneous quantum simulation and unbreakable quantum networks is right around the corner. The honest takeaway, the one the researchers themselves are trying to communicate, is more measured and, in its own way, more exciting than any of those exaggerated headlines. We have crossed the threshold where quantum technology stopped being primarily a question of scientific possibility and became primarily a question of engineering execution. That is precisely the threshold classical computing crossed in December of 1947. And history tells us what tends to happen after a threshold like that gets crossed. It doesn't happen instantly, and it doesn't happen for free, but it happens. Slowly, then suddenly, patiently, then all at once, a strange laboratory curiosity becomes the invisible infrastructure underneath an entire century. If the researchers behind this paper are right, we are standing at the very beginning of that same long arc, watching quantum technology take its first true steps out of the physics lab and into the world of serious, sustained, collaborative engineering. It won't look dramatic from the outside for a while. Most of the real transistor-era history didn't look dramatic from the outside either. But the physicists who understand what's actually happening beneath the surface are telling us, in the pages of one of the most respected scientific journals on Earth, that this is the moment worth remembering. Not because quantum computers changed everything overnight, but because this is the exact point in the story where everything that comes next became possible.